Welcome to the Deep Dive, where we try to cut through the complexity of architecture and really give you the core knowledge you need. Today, we are tackling something truly foundational for network organization, VLANs and trunking. This stuff is basically what turns, a potential mess of cables into an efficient, secure, and actually manageable system.
Yeah, absolutely. If you've ever dealt with a network, maybe more than just a handful of computers, you hit this problem fast. Everyone's plugged into the same physical switch, but, well, some groups have to be kept apart.
Right. You can't have finance seeing marketing's huge video file traffic, or worse, mixing with the guest Wi-Fi network. That's a security nightmare.
Exactly. So the question is, how do you take one physical box, one switch, and make it behave like, say, 5 completely separate little networks?
And critically, without rewiring the whole building. It's done through configuration, right? Let's set up our analogy for today. Think of that network switch as a big office building.
A multi-story office building, yeah. The physical structure, the building itself, that's fixed. But inside, you create departments. A VLAN, a virtual local area network, is basically just that, a department. VLAN 10 could be HR, VLAN 20 is finance, maybe 30 is for your servers. And the key thing is, even though they're all in the same building, sharing the same physical infrastructure, they are logically separate.
Okay, so there are like different floors or secured areas within the same building.
Exactly. And then, once you have that separation inside one building, you need a way to connect those same departments across multiple buildings, right, if you scale up.
Ah, okay. That's where trunking fits in.
That's trunking. If HR in building A needs to talk to HR in building B, the trunk is like the special hallway or maybe a dedicated elevator system that connects those specific departments across your different switches, your different buildings.
Right, carrying only the authorized traffic between corresponding departments.
Precisely. So our mission today is to really unpack how those invisible walls work, understand why that separation is so vital for security, and then figure out how that trunk connection manages to carry all these separate networks at once without mixing everything up.
Okay, let's nail down the definition first, because this is core. A VLAN is a logical segmentation of a single broadcast domain.
Yes, and that phrase, single broadcast domain, is super important. Think of it this way. If your computer is in VLAN 10, and mine is also in VLAN 10 on the same switch, we can talk directly. Easy.
Like we're in the same small office, just us.
Exactly. But, and here's the crucial part, if your computer is in VLAN 10, say HR, and mine is in VLAN 20, maybe finance.
On the same physical switch.
On the very same switch. We cannot communicate directly, period. The switch port configuration creates an intentional barrier, an absolute stop.
So that's the security kicking in immediately.
It is. And that separation fundamentally changes how network noise, like broadcast, propagates. See, without VLANs, it's just one massive flat network. One device sends a broadcast message.
Like asking who has this IP address.
Right, like an ARP request.
Yeah.
And every single device on that entire switch has to stop, listen, process that message, even if it's not relevant to them.
Which sounds incredibly inefficient. So these invisible walls are both for organization and security, really.
Absolutely. And this intentional separation brings 3 main benefits. These are the reasons VLANs are basically mandatory in any serious network setup. Better security, much higher performance, and just plain easier organization.
Okay, let's dig into security and performance a bit, because sometimes they feel a little abstract. You mentioned broadcast traffic. How big a deal is the performance hit without VLANs? Is it just tiny delays, or does it actually slow things down noticeably?
Oh, it can be very noticeable, especially as the network grows. On the performance side, think about those ARP requests we mentioned. They happen constantly.
Yeah.
If you have, say, 500 computers on one giant flat network.
Which isn't uncommon in a medium business.
Not at all. So every time one computer sends a broadcast, all 500 have to pause, receive it, look at it, and then decide if it's for them. It chews up CPU cycles on every single machine.
That sounds exhausting just from a device perspective.
It really is. Now split those 500 devices into, say, 10 VLANs of 50 devices each, maybe HR, finance, marketing, etc.
Okay.
The size of each broadcast domain shrinks dramatically, by 90% in that example. Now, when someone in HR sends a broadcast, only the other 49 devices in the HR VLAN need to process it.
Much less noise. It frees up the devices and the network itself.
Instantly reduces network chatter, frees up CPU on the computers, and makes the whole network feel more responsive.
To the security angle, that seems even stronger. A broadcast domain isn't just about noise, it's an attack surface, right?
Absolutely. The containment you get is huge. Think about something like an ARP poisoning attack. A malicious device tries to impersonate another machine to intercept traffic.
Nasty.
Very. In a flat network, that attacker potentially has access to intercept traffic from every single device. With VLANs, that attack is contained. If the attacker is in the marketing VLAN, they can only really mess with other devices in that marketing VLAN.
So the damage is limited. It's like containing a fire to one department instead of letting it spread through the whole building.
Exactly. Mandatory damage control built in.
I also see the organization benefit more clearly now. Instead of tracking things by, like, switch B, port 3 goes to Bob in finance, you manage it logically. This port belongs to the finance VLAN.
It makes managing the network incredibly flexible. Let's say the whole marketing team moves from the second floor to the fourth floor. You don't have to recable anything. You just go into the switch configuration for the ports on the fourth floor and assign them to the marketing VLAN. Their network access, their security rules, their performance settings, it all moves with them logically.
That's efficiency. You're managing functions, not physical locations.
That's the goal. So that core idea, separation for security, efficiency through less noise, and flexible organization. That's why understanding VLANs is absolutely critical for any network professional.
Okay, makes perfect sense. We've segmented our building. But now the inevitable happens. The company grows, we get a second building, switch B. How do we make sure HR on switch A can talk to HR on switch B?
Right, and crucially, without accidentally letting finance overhear HR's conversation, or vice versa.
We need that special connection, the multi-department connector, the trunk.
Exactly. The trunk port is where the coordination happens. We need to be really clear here. There are two main types of switch ports.
Okay.
First is the access port. That's what your computer, your printer, your IP phone plugs into. An access port is assigned to and carries traffic for only one specific VLAN.
So that's like the standard office door, and it only leads into one department, say the HR department on the third floor.
Perfect analogy. Then you have the trunk port. A trunk port is specially configured to carry traffic for multiple VLANs all at the same time, specifically between switches or maybe between a switch and a router.
Okay, so that's the super elevator or the main corridor connecting floors and departments, designed to handle traffic from everywhere.
Precisely. It serves multiple departments, moving people or data between different physical locations, like between our two switches, SW1 and SW2.
But wait, if that single trunk cable is carrying data packets from VLAN 10, HR, VLAN 20, Finance, VLAN 30, Marketing, how does the receiving switch, SW2, know which packet belongs to which VLAN when they all arrive mixed together?
That is the critical technical piece. It's solved by adding a tag. It's an international standard called 802.1q tagging, sometimes just called .1q.
Okay, 802.1q, let's break that down. What actually happens to my data, my Ethernet frame, when it's heading out onto that trunk line?
So as your data frame is about to leave the first switch, SW1, through the configured trunk port, the switch performs a little magic. It inserts a small extra piece of information, a 4-byte header, right into the Ethernet frame itself. This is the 802.1q tag.
4 bytes. Tiny but important. What's in it?
The most important part is a 12-bit field called the VLAN ID, or VID. This ID number, like 10 for HR or 20 for finance, is put into that tag. So the frame now carries its VLAN membership card, essentially.
Got it. So the tag acts like a digital badge saying, I belong to HR or I belong to finance.
Exactly right. That tagged frame travels across the trunk link. When it arrives at the trunk port on the receiving switch, SW2, the switch looks at that 802.1q tag. It reads the VLAN ID, say, 10.
Okay.
It now knows this frame belongs to VLAN 10, HR. It uses that information to know where to forward the frame within SW2. And then just before sending it out the access port towards the destination HR computer,
It does what?
it removes the tag. It strips that 4-byte 802.1q header off.
So the end device, the computer, never even sees this tag. It just gets a normal Ethernet frame.
Correct. The tagging is purely a switch-to-switch or switch-to-router communication mechanism. It's totally transparent to the end devices, but absolutely essential for keeping the traffic separated on that shared trunk link.
Wow, that's pretty elegant. A small tag enables this whole system of extending logical networks across physical boundaries. Without it, chaos.
Complete chaos, or just no communication. And this technical detail, the 802.1q tagging, is why configuring trunk ports correctly is so critical. If you forget to set a port as a trunk, or if the switches don't agree on how the tagging works, devices in the same VLAN but on different switches just won't be able to communicate.
Or worse, maybe traffic ends up in the wrong VLAN somehow.
That can happen too, depending on the misconfiguration. It leads to security breaches or just broken connectivity. Order relies on that tag.
Okay, let's apply this. Our two buildings, SW1 and SW2. HR is VLAN 10 in both. Finance is VLAN 20 in both. A PC in VLAN 10 on SWB1 pings its counterpart, another PC in VLAN 10, but over on SW2. That ping packet hits the trunk port on SW1.
It gets tagged with VLAN ID 10.
Travels across the trunk link.
Arrives at SW2's trunk port. SW2 reads the tag, sees it's for VLAN 10,
Removes the tag.
and forwards the normal Ethernet frame out the correct access port towards the destination PC in VLAN 10 on SW2. The ping should succeed.
And that's called inter-switch VLAN communication.
Real exactly. We've successfully extended the VLAN 10 broadcast domain across 2 physical switches.
Now, what about other types of traffic? Sometimes you hear about voice VLANs, for instance. How do they fit in?
Good question. That's a great example of leveraging VLANs for more than just basic separation. Voice over IP phones, VoIP phones, are really sensitive to delays, right? Jitter and latency, call quality.
Yeah, robotic voices, dropped calls.
Exactly. So best practice is to put IP phones into their own dedicated voice VLAN. It's just another VLAN, say VLAN 50, but it's specifically for phones.
Okay, why do that?
Because VoIP traffic packets are usually small but need high priority. By isolating them in their own VLAN, the network admin can then apply specific quality of service, or QoS rules, just to that voice VLAN.
So you can tell the switch, hey, if you see traffic tagged for VLAN 50, give it priority. Let it jump the queue.
Precisely. You ensure that the marketing team downloading huge files doesn't interrupt the CEO's important conference call. It's about using that logical separation not just for security, but also to manage performance based on traffic type and importance.
So you're organizing by function and priority, not just department. Very powerful.
It really is. It adds another layer of control.
Okay, let's loop back to that critical fail-safe point, the absolute barrier. We confirmed PC in VLAN 10 on SW1 can ping PC in VLAN 10 on SW2 thanks to the trunk and tagging.
Yes, successful inter-switch communication within the same VLAN.
But now let's take that same PC in VLAN 10 on SW1, and it tries to ping a PC in VLAN 20 finance, which is plugged into the very same switch, SW1. No trunk involved here, just trying to cross the streams internally.
What happened?
Well, based on what you said, the ping failed.
Every single time.
Yeah.
The packet goes from the PC to its connected access port on SW1. The switch looks at the destination address, determines it belongs to a device in VLAN 20. And the switch knows VLAN 10 and VLAN 20 are different broadcast domains. Its fundamental rule is do not forward traffic between different VLANs unless specifically told otherwise by a router. So it just drops the packet.
It enforces the segregation, full stop.
That separation is absolute at the switch level.
Yeah.
It's the intended behavior, the core security principle of VLANs.
So the switch itself cannot bridge that gap. It needs external help.
Exactly. That external help, the device designed to connect different networks, and different VLANs are effectively different logical networks, is a router, a layer 3 device.
Okay. So if finance needs to talk to HR, you absolutely must have a router involved to handle that communication between VLAN 10 and VLAN 20.
Correct. The router makes the decisions about if and how traffic should pass between those separate logical networks.
All right, I think we have the full picture now. VLANs create the secure, efficient departments within the switch. Trunking, using 802.1q tagging, lets those departments span across multiple switches.
And critically, the switch enforces strict separation between VLANs by default.
Let's do a quick knowledge check then for everyone listening. These seem like the key takeaways. What kind of port connects a single end device, like your laptop?
That would be the access port, configured for just one VLAN.
Okay. And what's the essential protocol, the standard, that adds that identification tag to traffic going over a trunk link?
That's the 802.1q standard, adding the VLAN tag.
Got it. And the big one, can two devices in different VLANs, say VLAN 10 and VLAN 20, talk to each other if they're just connected to switches with no router involved?
Absolutely not. They're completely isolated at layer 2.
Excellent. So we've really established how VLANs act like those secure departments, letting one switch handle multiple virtual networks efficiently, and how trunks extend these across a larger physical setup.
It's all about creating that intentional separation first. That's key for security and performance. And then figuring out how to connect things in a controlled way when needed.
Right. Separation first, connection second.
And, you know, that intentional separation is great for security,
Yeah.
but as we just discussed, it also stops potentially necessary communication.
Mm-hmm.
We know we need a router to bridge VLANs.
Mm-hmm.
But routers don't just work on VLAN IDs. They work on IP addresses, subnets, routing tables. It gets more complex.
So bridging that gap correctly is the next challenge.
Exactly. So here's something to think about. If we've done a perfect job separating HR, VLAN 10, and finance, VLAN 20, using VLANs and switches. What specific, potentially complex IP addressing schemes and routing rules do we need to set up on that router? How do we configure it so it can securely pass an important report from HR to finance without accidentally breaking the very separation we worked so hard to create with the VLANs in the first place? The router needs to understand the language or addressing of both those separate worlds.
Ah, I see where you're going. The router needs a map, essentially. A logical map that corresponds to those virtual networks.
Precisely. And building that map, understanding how to assign logical addresses to these different virtual networks and how routers use that information, well, that hinges entirely on mastering IP addressing and subnetting.
That's the foundation for solving the puzzle of secure inter-VLAN routing. A perfect place to leave off for today. Thanks for joining us on the Deep Dive.